Okay. Today, talk about medium access control. This is the one that probably has got more to learn about in wireless than most. And the activities that you're going to do at the end, I've got the CDs up here for you to do that. The first one, it says to have you make a bootable flash drive. If you want to do that, feel free. Well, we've got the CDs up here, which will be easier to use in class because we shouldn't have to go through the credentials in order to boot, because I think most of them are set, most of the machines are set up that if you boot to a flash drive, you got to put in administrator's credentials, and that's the local administrator. Might work with yours, but the CDs are here if you want to make it, and I recommend Kieran's Yummy utility instead of the one that he talks about in the book, the Umbooten, or whatever it is. But medium access control. Why is medium access control such a big deal in wireless?
Because only one person can talk on the channel at a time.
Because only one person can talk on the channel at a time. Until we get to the N standard. Then with beamforming and things like that and multiple radios, the MIMO, multiple input, multiple output, we can have more than one connection at a time. But he's absolutely right. What's the other issue with medium access control? Can all of the stations see all of the other stations all of the time?
Not if it's a hidden node.
Not if it's a hidden node. What's a hidden node?
Well, one station can't see the other station.
One station can't see the other.
But the access point can see both stations.
But the access point, exactly. What if we had an access point in this room that had an omnidirectional antenna, and we went as far as we could go, the 100 meters in one direction, assuming that we could actually connect that far away, and 100 meters in the other direction, both of the stations can see the access point. It can control traffic, but they can't see each other, as James said. And what happens if they both broadcast at the same time? Say again? Access point, don't know who to listen to. If that happened to us in Ethernet, what would we say we had? Jam signal. We had a collision, we sent a jam signal. So in wireless, you use collision avoidance, and there are some techniques available at layer 2 that you're going to need to know about for collision avoidance. Collision detection, relatively easy. You send it out, listen. If there's a collision, you send the jam signal. This one becomes a little bit more complex. So the objectives: describe 3 WLAN service sets, wireless LAN service sets. What's a service set? Basically, in the simplest terms, it's an access point or a workstation if we're in the ad hoc mode. So we're going to have 3 different types of service sets that are available. The features of the MAC frames and the MAC frame types. This is where, if you really want to keep this up straight, you may want to make yourself some notes, however it works for you. Make yourself some tables as to what does what when, because we're going to have 3 official and kind of 4 different types of frames that are available in here. The MAC functions of discovering, joining, and transmitting on a wireless LAN. How are we going to get connected to it? And once connected to it, what happens if we get in and out of range if we have multiple access points when we go up here to the extended service set? What's going to be the advantage of these things? The service set is all the devices that are associated with an 802.11 wireless LAN. So what we can have in here, and we'll go through each of them a little bit, are 3 different types of service sets. And they are what, Dante and Carrie? What kind of service sets? What is a service set? What is a service set? That's right there. What's a service set? Huh? All of the devices. What are the devices that we use? Access point, phones. What can a phone be? An access point or a station. If we go back to early on, what is a computer? What was it called? This was like week 1, wasn't it? Station. And what did we connect to? An access point. Can a computer be a station? You had that piece of software that kind of worked and kind of didn't work. Connectify Me did kind of, right? Kind of, sort of. It actually could get connected, but what did it do? It became a router. So what did it do? Became an access point. Is that something that you necessarily want to happen? And then we have the access points that we go out and buy. And then if we have a wide area like in this building, when you look at Skynet or SkyCart, or when we look at Skynet or SkyCart, we've kind of looked at it, kind of hadn't looked at it. How many access points are there available? Any idea? 3. There's 4 now. Don't know why you need 4 in a building this size, but there are 4 different access points available. Why do we need 4 different access points? Roaming, coverage. One of the things that does happen in this building, site surveys sort of thing, and site surveys are next time. When you go in the very back of the building, there's a physical firewall. The physical firewall blocks the signal from this part of the building to that part of the building. So you would need those. Would you want to have to, if you're using a tablet, walking around with a tablet, would you want to have to re-authenticate every time you went from one to the other? Probably not. I wouldn't if you're roaming around. And if you're in a larger campus where you can go greater distances, that is something you don't have to do. It maintains your connection. It's called roaming. What it allows you to do is go from one access point to the other and maintain your connectivity. The different types are the basic service set, the extended service set, and the independent service set. A lot of fancy names. A basic service set is, any guesses? Yeah, try my thing.
One area. It's just one area.
One area. It's one access point. Well, that worked well, didn't it? So it is an access point. An extended service set. Multiple access points. And here's my favorite, independent basic service set. 2 stations talking to each other. Independent basic service set, we call it ad hoc mode. Ad hoc mode is when you set computers up without an access point so that they can communicate with each other. And unless you have something to do sharing outside, say again? Like a bus connection. But with like a bus connection that can't go anywhere. If you set them up in ad hoc mode, and we unplugged all the wired connections in this room and configured the wireless NICs for ad hoc mode, they could all talk to each other. But unless you had some sort of internet sharing on one of the machines, then you're not going to go anyplace else. Ad hoc mode allows the machines to connect together. Necessarily a good mode, I don't know, it's there. So the ones that we really, I think, kind of care about are the basic service set and the extended service set. The extended service set is more than one. You take 2 or 3 or 4 access points and put them together, all named the same in the SSID service set identifier term that will come up here in a minute. All the same one allows you to go from one to the other so that you can share things. These are going to all be connected at some point to a wired network, as you've seen these access points. to go anywhere, we can connect them all together on an access point, but to get any place, we either need something to allow us to go someplace else. Typically, what basic service sets, extended service sets, all the service sets are set up for are to allow the wireless connections to get onto your wired network, because that's where most of the information is. Most of the things that we're going to use are. So the basic service set, group of wireless devices served by a single access point. So when we connect, if we set up our access point, everybody connected to it, that'd be the basic service set. As a basic service set identifier, the BSSID is the MAC address. We're going to have two names for these things. One's going to be the SSID, whatever we call it, Room 111, Skynet, SkyCart. The other is going to be the BSSID, the basic service set identifier, which is the MAC address of the access point itself. That can become significant when you're monitoring what's going on, and if you want to see which access point you're actually connected to, that's the only way to determine it in a roaming environment, because they're all going to have the same name. They're all going to be connected to the same network, same SSID. The basic service set must be assigned a unique identifier, the service set identifier. The ones that we buy come with a default, right? D-Link, Linksys, Netgear, whatever else. And one of the ways that a lot of people determine if people have the default still configured on their wireless access points is, what's the name of it? Has it still got the default? And if it's got the default name, what are the odds that it's still got the default password? Probably pretty good. And those are clearly available. So we have this thing. What this really does serves as the quote network name. What this does is when you're advertising these things, it tells you which one you want to connect to. And if you go into this network, one of them you can connect to, Skynet, SkyCart. Skynet, I think we can connect to. SkyCart, it's got a password that I don't know. Maybe somebody else does. But which one do you want to connect to, Skynet or SkyCart? So it's the network name. And if you're in let's put us in an apartment building, how many of them do you see out there? Which one do you want to connect to? The one that's not secure, probably to yours. Legally, which one do you want to connect to? Your own. So we need to know the name of it. And that's what those do. The basic service area is the geographical area. It's how far out it goes. And we'll get into some surveying, talk about some surveying next time, site surveys. How do we determine what's the basic service area? The basic service area in here, if we put an access point in the middle of everything forward of the firewall, it probably serves it pretty well. So that would be the basic service area. Theoretically, range-wise, it should go behind the building, but or behind that firewall, but it's not going to happen because of the firewall. So the basic service area, the geographical area, where can it go? And it talks about here the maximum for the WLAN. Depends on many factors. What would some of those factors be based on what you've seen, done, talked about? Interference. Density of the wall. What kind of material? Because you had the one, and yes, I know it's kind of hard to find some of those densities. Drywall. How much does it stop the signal? Some. Cement. Probably more. What if we did rebar, steel bars and cement? A lot. So those are some of the geographical, or some of the factors that are going to depend on these things. How far away is it? What's the signal strength? What kind of antennas do we have when we do those things? Dynamic rate shifting. What that means is the farther you get away from the access point, what happens to the signal? It gets weaker because of, try to get these terms back in. Attenuation. Free Where's that magic word?
Free space loss.
Free space path loss, right? What that means is attenuation, all the same thing. The farther you go, the weaker the signal. The weaker the signal, slower the data rate. So when you're in a business environment, might you want more than a basic service set? Something you have one that the person in the corner office, probably going to be the CEO or somebody, gets the slowest data rate. I mean, you may or may not be using wireless for those things, but if you are, and there are a number of reasons that you would use a wireless, obviously. So this is the basic service set and the basic service areas. Inside the circle here, we've got the access point and the two machines with their antennas and everything is right with the world here. Notice that the basic service set connects to your wired network, and that's typically what's going to happen to these things, because how many people are using wireless to get actually out of their network? Some people are. Some people can only get wireless internet, for instance. Then you would be using, but you probably have a wired network to get it there. Here, where does the wireless go? To the internet, I know. But it goes onto the wired network. It goes onto a VLAN that goes to the internet. So, basic service set, one of these things, one access point that the machines connect to get to the wired network. Theoretically, you should be able to get to a lot of different things. Extended service set is two or more basic service sets. So what you're really talking about is an extended service set are two access points that have the same SSID in simple terms. Why would we want to do that? Extend the range. What if we want to extend wireless to the back of the building? How would we do that? Another access point back there. And that access point is going to be connected to the wired network. The access points don't relay information to each other. That will happen in some configurations, but not in the extended service set. APs can be positioned so that the cells overlap to facilitate roaming. And roaming happens automatically. It's not anything that we do. When certain things happen, the signal strength gets low, you get a lot of error messages, you don't get all of or enough of the signal, then it'll automatically look for shift to the stronger signal. The clients are going to try to connect, because if they go through the other processes that we'll look at here in a few minutes, try to connect to the access point with the strongest signal. Is that necessarily going to be the one that's physically the closest to you? No. Strongest signal affected by all those other things. So the wireless chooses the AP based on the signal strength. While moving, if the mobile device finds an AP with a stronger signal, the device associates with it in a process called a handoff. Layer 2 roaming occurs between access points on the same subnet. One of the things that happens in roaming is the 802.11 standard doesn't really define roaming. So when you get into these things, into roaming, the recommendation is if you start with one type of access point, you stay with that access point, because there's no real, it's kind of what it is, roaming, you go from one to the other, but there's no definition on what actually makes roaming work. So the two access points, if you were having overlap, this probably isn't enough the way this one's drawn, because as you get to the end of the basic service area, I'll try to use the terms too, what's going to happen to your signal? In here close, we're going to be 54, 36 on down. Until we get to the end, we're going to be at 1 or 2 megabits per second maybe. And if you go from one that's 1 or 2 megabits per second to the other one, is that such a big deal? There's some point, so, and they have definitions, how much overlap should you have in order to be able to make this work effectively? Because you want the transfer to take, the handoff to take place before you get into those lower data rates. So you're really going to have these things moderately close together, and I guess that's why they put 4 in here. We had 3 before, but when they put the new access points in, they put in 4. The router separates the APs on each of each AP resides in a separate subnet. A new IP address must be assigned layer 3 roaming. The one before is layer 2 roaming, where he just looks for the strongest signal. Layer 3 roaming also is going to require some configuration on the router. You have to set the router up so that it knows that roaming's taking place, so that it can do these things. What you're going to get is on your network, when you connect, you're going to get an IP address on that subnet. Will that IP address work on the next subnet? Now, what happens is when you roam from one layer 3 network to another layer 3 network, the next one gives you what's called, the router gives you what's called a care of address. And the care of address is registered, and then it creates a tunnel from your network to that access point, so that you don't change the IP address, but you get another IP address, the care of IP address. Mobile IP is the mechanism that has to be set up, and mobile IP has to be supported by and configured on the router before it can do these things, the router that separates the 2 access points. And I looked at a bunch of them, and it says that the 2600s, which we have some of them back there, support mobile IP, so should be able to set up layer 3 as well as layer 2 routing, should you want to do that. The mobile IP to computers are given a home address, a static IP. The home agent's the forwarding mechanism that keeps track of where it's located. The home agent's supposed to keep track of its subnet. Where are its access points? Are they all on the correct subnet, the original subnet, or have they roamed someplace else? When the computer roams to another network, the foreign agent provides a routing services to the computer. So the agents, these home agents and foreign agents, are the things that have to be configured on the router so that the router can keep track of what's going on with the devices. The foreign agent assigns a temporary IP to care of address. It's kind of like if you went on for a month someplace and you're going to get your mail sent to you. You would be forwarded to you in care of whoever the permanent address was, so that the mailman didn't send it back, so they don't live here. So the care of address is assigned temporarily while you're on the foreign network. Computer registers the care of address with its home agent so that it knows where to send the information. Again, much like you would do with mail. Mobile IP, when the frame is sent to the computer's home address, the home agent intercepts it, encapsulates it. And when you see encapsulation and tunneling, think of those things together, because how did a point-to-point tunnel work? We encapsulated it with an address that could get there. We encrypted the whole packet, encapsulated it, and sent it there. So if we encapsulate that frame into a new frame with a care of address, what we're really doing is putting the new address on to send it there. When it gets there, that address can be stripped off. When it gets to the machine, that address can be stripped off, and it's delivered to the original IP address. Seems like an awful lot of effort, doesn't it? It does to me. I don't know. It just seems like an awful lot of processing effort. Well, what could you do when you got to the new one? If you had these things separated, if you could get a new IP address, then it wouldn't have to go through all of this. But this keeps the machine on its original subnet and allows the traffic to still get there.
A lot of one-stop functions, when you register it with address, it's stuck on
there. That's true. That's true. There are some functions when you register with an address, that's the address that it wants to use. Redirects the foreign agent, which send it to the computer located in the foreign network. So again, registration, and this work's all being done on the router. Remember, this one is when 2 access points are on different subnets connected to a router. The router's going to route the information. The mobile IP's got to be configured on the router so that it knows where to send the information. Same picture basically. The BSS ID 198.146.118.10 gets this address. 210 and BSS ID. These are the subnet addresses of these things. The subnet's 198.146.118-1. The IP address of the BSS ID, the IP address of the access point of each of these things, and then the router configured to handle mobile IP. I think probably with telephones it'd be more significant. Well, the way people use smartphones now, probably would be more significant which network you're on. It also would allow you, with some more configuration, to be able to kind of keep track of where people are, wouldn't it? Which area are they in? It wouldn't locate them, you know, to the nearest 15 feet, but it will locate them to an area so that you would know maybe what building they're in. If they go onto this switch or this access point, you know that they're in building whatever, or what part of your building they were in. The distribution system used by the AP to determine what communication needs to take place with the APs. Fancy word in the ESS or with the wired network. Fancy terminology for it determines whether it needs to be sent out over the wireless or whether it needs to be sent out over the wired. Is it to a machine that's one of the wireless clients, or does it need to send it someplace else, to the internet or wherever else? Decide if it's necessary to exchange frames in their own basic BSSs with the wired network, or to forward the frames to another basic service set. When you think about this, and when you look at the wireless packet, it's got a lot of stuff. It's radically different than the 802.3. The structure is the same and just more stuff in it, because you need more stuff in it. For instance, you know what frequency it is. That has to be marked. Whether it's frequency hopping, what kind of framing, what are we doing with the thing? Is it OFDM? Is it direct sequence spread spectrum? Is it frequency hopping spread spectrum? So when I say there's a lot, and there are a lot of things that can be selected, but there's nothing magic about it. It's all things that are there. Is it available? And a lot of it is this service, is this available on the access point? What speeds does it support? Got to know all of those things. Station can't, if it doesn't support the speeds of the access point, then they won't be able to connect. So those things have to all match up. Just like when we talk about encryption, you got to have the same type of encryption. You got to have the same things supported on both ends before it's going to work. The distribution system media that interconnects access points, and typically that's going to be wired unless we're in a mesh environment. Mesh, if these things are connected in a mesh, then the wirelesses are going to connect to the wireless. But at some point, you still need one access point that connects to the wired network so that you can have access to your resources. The wireless configurations used to connect the AP is called the wireless distribution system, the WDS. That's one of the terms that you're going to see in these things. And there's a lot of terms that are new, I know that. WDS, wireless distribution point. How are we going to distribute the wireless signals, what you're really talking about there. The independent basic service set, infrastructure mode, wireless network that communicates through an AP. Infrastructure mode, AP, and the infrastructure mode would be the basic service set, the independent basic service set, not the independent, basic service set and extended basic service set, access points. When we don't use the IP, the peer-to-peer, when we don't use an access point, it's going to be called ad hoc or peer-to-peer, computer to computer. We can do that with computers on a wired network, can't we? Well, we just hooked them all up to a hub or a switch. Would they still work? Would they go anywhere? Nah. Same thing with wireless. We can hook them up all together. It's going to be slower. Those networks are going to be slower than an access point. And something has to eventually say, yes, I'm it. Basic service set's more flexible than the independent, being able to connect to other wired or wireless networks, because if we're using ad hoc, and you can use ad hoc, the router, the virtual router, which I know didn't work, except for some people that did it at home, there's something stopping it on the machines in the building. Or the Connectify Me, you could share the wireless, couldn't you? Didn't allow you to, maybe not as straightforward, but there were two connections. One's the wireless and one, what do you want to share? You can share your wired connection with the users that connect to you wirelessly. If users connected to you wirelessly on your computer, then that's going to be ad hoc mode. Ad hoc mode, computer to computer, infrastructure mode, we're looking for access points. Quickly setting up a wireless network where no connection to the internet or an external network is needed unless you're going to use one of the other connection sharing features that are available. Windows has a lot of connection sharing available in it. A picture there, the independent basic service sets, computer to computer, and that's what we're really talking about there. So 3 types of service sets, right? Basic, which is single access point. Extended basic is multiple, more than one access point. And independent basic, ad hoc computers, computer to computer independent basic. Because I guess maybe one of the ways to remember that is it's independent of an access point. Tell you what, before we start the frame formats, let's take a break. Okay, so let's look at these frame formats a minute, and you've got an activity, and that's why we have the CDs, that you boot to them and configure it in Linux so that you can look at these things after we talk about them. I've got some other ones that I've got some captures on if you don't get all of the different ones that you can look at. You may not in here, for instance, a probe is going to be something that advertises the access point. And the probe, when we send a probe out, it advertises the SSID. And then if you've got a probe request, you ever configure your device to go to a particular access point? I mean, you go to a hotel and you hook up to it and then it stays there. And then you go to another hotel, and that's why I can show you some of these things, because the devices just had some stuff there. And you try to connect to a particular one, it's going to have a probe request and a probe response. So a probe, passive active scanning is what we're going to call it. And then you're going to have data. We're going to be able to send data. And then we're going to have what's called a null data frame. And the null data frame tells the access point that the device is going to sleep. And the higher priced access points, once the device goes to sleep, will cache any traffic for it. When it wakes up, it will send it to traffic. So we're going to have management frames, control frames, and data frames when we look at these. 3 different types of frames. And when we had 802.3, we had how many types of frames? 1, right? 802.3. Everything was in that. This one's going to have 3 frame types in order to make this thing work, because we got to get onto the network. Once we get onto the network, we got to get access to the media. Once we get access to the media, we'll send the data. Once we send and receive the data, we're going to have to acknowledge that data. So these things divided the data link layer into 2 sub-layers, same ones that we had before, isn't it? Logical link control had this in 802.3, LLC, and Mac. So we still have these things. Functions performed at the Mac sublayer and involve different frame types. Logical link control, a common interface, reliability and flow control. Common interface as it goes up to layer 3. OSI model uses the term data unit to describe sets of data that move through the OSI layer. And what we're going to have here, when the data moves into the MAC layer, it's going to be encapsulated. It's going to get its name. Everything's got a name. It gives, I think what it does is give all these testing agencies something to ask questions about. SDU, service data unit, specific unit of data that has been passed down from the higher layer. So any layer of the OSI model can have a service data unit. If we pass it from layer 5 to layer 4, it's going to be data at layer 5, and it's going to be a service data unit at layer 4 when it gets encapsulated. So all that means it's been passed down to the lower layer, but has not yet been encapsulated by that lower layer when it gets there. Protocol data unit specifies the data that will be sent to the peer protocol layer. What does that mean? If we have IP at layer 3, what's it going to send to layer 3 at the other one, at the peer one? IP, we hope. What that's saying is you got to be talking the same at each layer on the different devices. So protocol data unit, and the protocol data units, if you go back to them, an acronym that I learned in one Cisco classes is, and if you start with the data, because the data, you're going to have data at the top layers, right? So you can have data, some people fight back. Data, transport segment, people will be a packet, a network packet, fight, data link, frame, physical B bits. So what are the protocol? Those are the protocol data units. And actually, instead of data, you can call it data, but data is what's going to go down and get put into the protocol data units. Some people fight back, starting at transport, working your way down. Changing the SDU to PDU involves the encapsulation process which the lower layer had. So, and then we're going to call it A. When we do that, it's going to be a PPDU. So 802.11 network uses the SDUs and the PDUs. The layer 3 sends it to the LLC layer. The unit is called a MAC Service Data Unit, MSDU, and the LLC data sends the unit to the MAC sublayer where the MAC header is put on it. Then it's going to be called an MPDU. Nothing really magical there. So MSDU, and then we encapsulate it, and it's going to become a PDU, MAC layer PDU. Also known as a frame. The MPDU is sent to the PLCP. That's last time. That's the physical layers divided into two parts. So the PLCP sublayer and the physical layer makes it a PSDU, and the PSDU passes it down to the PMD, and it's going to be called a PPDU. The P is PMD. It got to be too many letters. PMD, PPU, PPDU by adding the header and the footer. And the PPDU is then transmitted as a series of bits, ones and zeros. So all of this encapsulation as it goes down the chain. Pretty good, I think, here. The MSDU goes to the MPDU, the PSDU, all those different clever letters. The SDU gets encapsulated, sent as bits, and then it gets de-encapsulated as it goes up. You just strip the headers off as it goes up the OSI layer. One of the things a MAC frame for aggregate MAC serial data unit. See, I told you this one is just crazy, and really sit down and take some time with a book or books. There are a number of places that these are called, and make yourself a table of these things. That's the only way I know how to do it, because there's just so many of them. What this says, aggregate, we said before, each of the packets that's sent has to be acknowledged. Every single one of them. Until we got to the later protocols. 802.11n allows for what they call aggregate MAC data units, which allows aggregation or putting together a number of these things and acknowledging more than one at a time. This acknowledgement down here is different from layer 4, TCP, and we talk about layer, when you and I did for a long time, acknowledgement. Well, we already have that built into TCP, don't we? The ACK. And we create this window size and we send a whole bunch of data and we acknowledge it. This is layer 2 acknowledgments. These are 802.11 acknowledgments. So that what's happening here is the receiving unit is acknowledging receipt of the layer 2 information. The connectivity at layer 3 is going to be, and layer 3 and layer 4 is going to be a separate issue. So this is all layer 2. The stuff that we're talking about here is all wireless specific, layer 2 specific items. Also allows multiple MPDUs to be combined. So what we're saying here is instead of having to acknowledge MSDU 1, 2, 3, and 4, they're put together. Instead of having 4 acknowledgments, we can have 2 acknowledgments, and then if you put those together, you can acknowledge all the data. It does have what's called selective acknowledgement, which says that you can acknowledge, if we sent this thing, we could acknowledge receipt of everything except one of them, and that would be the only one that would be resent. So it's a little bit smarter than having to send the whole packet over. So it can use selective acknowledgement. Interoperability, different systems can understand each other. One of the differences between 11 and 3 is the frame size, known as the MTU, the maximum transmission unit for 802.3 is 1500. One of the other things, and I know I jump around, something that may override this is the maximum transmission unit used by TCP, IP TCP. So it may override this thing. Other options to address interoperability, is it too big, too little, too whatever, because the frame size, 802.11 frame size, is larger than the 802.3. So fragmentation, dirty word, right? In TCP, fragmentation was a dirty word because what that allowed us to do was sneak fragments in. Again, fragmentation, if it's too big, it can be fragmented, broken up into different parts. Fragmentation, upside and downside. If you have to retransmit things and they're fragmented, you don't have to retransmit as much. Jumbo frames is another thing because we have this frame size that we've claimed forever, but the hardware that's available now allows jumbo frames. As a matter of fact, we use jumbo frames on the iSCSI connection from the server that runs the virtual machines to the iSCSI hardware, to the hard drive, because it makes things faster. It's the only thing on that traffic, so we set the jumbo frames to as large as the NICs and the switch will handle so that the transfer is quicker. Don't have a lot of loss there. Problem with jumbo frames is we made this thing big. What happens then when you have to start, if you have interference and you have to start retransmitting? Then you got a lot more data to retransmit. So each of these things has its advantages and its disadvantages. Jumbo frames send a lot more information at the same time. Jumbo frames, if we lose it, then we've lost a lot more information. Kind of like maybe moving stuff in a pickup truck or in a moving van. When you move from you went from apartment to house, right? Probably moved it a little bit at a time. Got a truck, big truck. What happens if somebody stole a big truck? All the furniture's gone. What happens if you do it in little bitty loads? Pickup truck, then you only lose that load. Same thing. same thing. Same thing. Lowest cost denominator is what these things should use. Differences between the high throughput HT and again more and more things. And when we added the N protocol, we added some other stuff. We had ERP, which was extended range physical layer in the 802.11bg area. When we went to 802.11, we have high throughput, higher data rates when we do these things. So there are 4 operations, and they're in the book. Greenfield mode, mode 0. I thought I wrote these down, but I didn't. Non-member protection mode, mode 1, 20 megahertz protection, and then mixed mode. And in the test bank, I have seen some questions about some of these things. So this one's probably worthwhile to look at. And what does each of mode 0? What does mode 0 mean?
That the devices operate at the same HT with the same
HT, let's see.
Perimeter.
High through output.
Roam into this BSA, it would not be able to access the WLAN. So what does that mean? That's a whole bunch of words. What does that really mean?
If somebody comes in with a G station, they're not going to be able to do it.
Means they're all ends, right? N has its own language. And when they talk to the access point in the N language, and the B's and the G's come in, they don't understand the N language. So Greenfield mode, mode 0, when we go through that thing, it says that all the stations in the BSS or ESS are 802.11n devices. So HT non-member protection mode 1, the HT non-member protection mode is the legacy mode of transmitting. All stations, including the N, use the A, B, and G format. So in this one, everything uses the A, B, and G format. Is that necessarily good? Is it? So we want to take our 802.11n 300 megabit per second access point and bring it back to 54 meg. But what that does is allows the backward compatibility for the legacy devices. The next one is about how much bandwidth we're going to use. Mode 2, all of the stations in the 20 megahertz protection mode are 802.11 HT devices. If 20 megahertz only HT device associates with the 2040 megahertz, the AP protection must prevent the 20 megahertz only station from transmitting at the same time. So what this has to do with the bandwidth, the 20 and 40 megahertz, protecting the 40 megahertz bandwidth. Well, what does it say? It says that if a 20 megahertz only device comes in, we're going to protect it from, then the protection must be used to prevent the 20 megahertz only stations from transmitting at the same time as the 40 megahertz stations.
So is it allowing it to transmit?
It's allowed to transmit, but only at 20 megahertz after the 40 megahertz is done, yeah. And it has to set up some sort of a mode. Mixed mode enables backward compatibility, does so at a price. The 802.11 devices must transmit a legacy format preamble followed by the HT format preamble. Remember the preamble, the legacy preamble was that really fast 1 megabit, right? So it has to transmit that just in case. This is a just in case something is there. The legacy preamble tells the A, B, and G devices to avoid transmitting over the HT frames and are sent to and from the 802.11n devices. What this is saying is that we want to, this is legacy, right? We want to allow these older devices on the network, but we don't want them to get in the way. So before the end devices start communicating as end devices, they're going to send a preamble that says, don't talk while I'm talking. Now what happens in the frame is when these things communicate, they tell everybody that they're going to communicate, and not only that, how long they need the media for. These got examples in the book about you're at an isolated cabin, you've got one telephone, and you have to stand in line to get the telephone, and then he's got the kids. The good kid, you know, gets a lower wait time than the bad kid, kind of deal. The access point, the stations, not the access points, the stations are going to get wait times, and those wait times are arbitrarily assigned. And that's one of the things that you should be able to see in the packets when you get there. The wait times, how long do you have to wait to get to the median? Because, as James said earlier, how many can we have connected at a time? Grand total of one, right? Kind of like, and it really is kind of like using the phone. The cell phone, you're in an isolated area. The cell phone, who gets to use the phone? Depends, well, who's controlling the phone? The parent. The parent. So the kid comes up and says, hey, I want to use the phone. What do you say?
Okay, get off.
As soon as you clean the room, as soon as you clean your room, right? And then the other one says, I want to use the phone. No. My boss is going to call within the next 20 minutes. You can't use the phone for 20 minutes.
So
Or,
it's like a token almost?
yep, kind of, except it's not nearly as efficient as a token. Because it's, well, polling is a separate entity. What you do is say, you got to wait this long. Well, first they announce that I'm going to use the media for whatever. And these things are called time slots, for however many time slots. And each of the protocols has its own time slot, the amount of time. So I'm going to use the media for this many time slots. Just to be sure, we're going to assign you a random number of time slots to add to that. So that theoretically, you could have been the first that tried to get there, and then somebody else comes in a little bit later and they get a shorter time slot. They may get the media before you do. Doesn't seem fair, does it? Which is a little bit different, kind of like contention. It is kind of like contention. And then we get into the issue, what if the A's and the B's don't understand this? What do we do? That's when we get into the request to send and clear to send type thing. You ask the access point, and it sends out packets that the BGs, A, B's, and G's would understand. So we have the three frame types. We talked about this a little bit earlier. We're going to have a management, control, and data frames. And we're going to have two types of data frames with data and data frames, null data, a null data frame, which doesn't have any data in it. Basically is telling the access point about the power settings of the device. So the management frames initialize communications between the device in infrastructure mode and the device, or between devices in ad hoc mode. And it's going to have the frame. The duration here is going to be the amount of time. More addresses, address 1 and address 2, and when we get into these things, they can have up to 4 addresses. The BSSID, sequence control, frame body, and a frame sequence check. So the header information and the size here of the header information is shown in this thing. So the management frames make the connection. How are you going to get connected to the access point? Management frames, authentication, association response beacon, a whole list of things, and you should see a number of these whenever you do the scanning that you're going to do. Authentication here, when we talk about authentication, what do you think of when we say authentication? Username and password. What are we talking about here with authentication? So authentication, username, and password in our sense. When you put an Ethernet computer on the network, what do you do? Dora, what do you put on the network when you want to connect it to the network? What do? Plug it in. When you put a wireless computer on the network, what do?
You said when you put a what?
A wireless computer on a wireless network, what do? You got to get permission to get on the network. The first thing that happens is authentication frame. And there are two types of authentication. The default's open. And what is open? What do you think that means? No questions asked. Anybody can get on it. The other one is pre-shared key, our favorite. Pre-shared key would be our favorite authentication protocol, WEP. You may or may not want to do that. 802.1x, which is a higher level of security, how's that for avoiding the word authentication? Depends upon open authentication, and that is the default. What we really are talking about mostly on these things is the ability to send packets is the encryption protocol in it that we use in these things. So once we authenticate, then we have to request association. And you get an association request and an association response frame. These basically say, yeah, you're on the right SSID. So you associate with a wireless network. Beacon frames, the access points send beacons, and they send them fairly quickly. You're going to see a lot of those, which basically says, I'm here. Deauthentication and disassociation frames are notification frames. You don't have to get permission to deauthenticate or disassociate. If you turn a machine off, that's going to happen. It's going to send it, but it doesn't wait for a response. These things, authentication, are going to have responses. A probe request frame and a probe response. A probe request is a beacon frame is going to be, I think we can call that passive, and the probe request and the probe response we'll call active. The passive is just sending information out. The active, we're looking for something specific. Reassociation request frame and reassociation response would be part of roaming. Because we already authenticated, hopefully we only had to authenticate once. When we go out of one access point into the other access point, you have to reassociate with the new access point. Control frames provide assistance in delivering frames that contain data. Receiver address and transmitter address. And again, the addresses that we typically have are source and destination, right? And that's it. But that may not be all we need. The frame control here we have, duration is going to be how long, it's consistently going to be the number of time slots. Receiver address, transmitter address, the radio addresses, and then the frame check sequence at the end to be sure that it didn't get destroyed or damaged en route. The data frame information is to be transmitted to the destination address. The frame, the duration is going to be the time, address 1, address 2, address 3, sequence control, address 4. You're typically not going to use all of these addresses, but they're available if you need them, and that was if you go from spot to spot. And then you have the data down here. Notice this thing goes up to 18496 in bits. So that's going to be larger than, the whole thing is going to be larger than what we would have with 802.3. So MAC layer, discover the wireless, joining the wireless, transmitting on the wireless are the things, and we talked about those a little bit, that we're going to need to do with this thing. So at regular intervals, sends a beacon, and the beacon just announces, sends on the radio its presence. Do you have to send the SSID in the beacon? No. Think you're going to be able to see it anyway? depends. Actually, it's going to be there at some point. You're going to be able to, once you get into monitor mode, which is why we have to use the Linux machines, you're eventually going to be able to send it. Provide information for other devices to join in its process known as beaconing. So we're going to send the beacon in the beaconing process. Forward allows a standard structure. The destination address is always set to all ones. What is all ones for the destination address? Broadcast. So this is going to be, and when you look at these things, you should see these things when you look at the scans that you're going to do in the activities. The beacon frame body, the beacon interval, time step, SSID, supported rates, parameter sets, and capability information. So all those things that you the workstation, the station needs to know is here in the beacon. Can you actually connect to it? If I had a B device and I had set my network up for G only, would it be able to connect? No, because it wouldn't meet all the parameters in the beacon frame, or shouldn't. In ad hoc, the networks, each wireless device assumes the responsibility for beaconing. They all can do beaconing in ad hoc mode. The beacon normally every 100, that's a lot, in every 100 milliseconds. You can change that on, not on my 1995 access point, but on the Cisco's and on the higher level ones, you can change that. Why would you want to change that? For both larger and smaller. Why you want it bigger? Bigger number would be, doesn't send it as frequently, right? Why would you want to do that?
Maybe you want to hide your network.
Maybe you want to hide your network. Maybe you don't want all that traffic on your network. Bogs down the network. They're pretty small, but you're right. That bogs down the network. Every 100 milliseconds quite often, quite frequent. Why would you want to make it smaller? Well, why would we want to make it 50 milliseconds?
Make sure everybody knows that the access point's there.
Access points there. What about for roaming? Can make roaming quicker, more efficient, whatever. 100 milliseconds to me is still pretty fast. But when we're talking about 2.4 billion things a second, maybe that's not so fast, huh? Must be looking for, the wireless must be looking for the beacon frames. The passive scanning, the wireless device simply listens, and that's when you turn on your laptop on the wireless and you see all these networks show up. Passive scanning, because they're advertising themselves. And the ones that you see the names of are advertising the SSID in the beacon frame.
It says other network.
Yeah.
I turned them off.
Did you turn it off? It says other network?
Yeah.
You see some of them around here, and you're going to see that occasionally, I think, in some of the stuff that you do in here, other network. Active scanning, the wireless device sends out the management probe request. And when I turn it on and I have configured it, and that's one of the things we did early on, you went in and configured it to go to a specific network, it's going to send out the probe request, and the probe response will come back from the access point. So probe request and probe response frame is looking for something specific. Unlike a standard wired, we have to do something with authentication. And what was authentication in a wireless network? What does it do? Authentication. It just simply says, okay, you can try to join. Does it mean that you're going to really be able to get an IP address and be able to do anything? Not really. Because if we have encryption configured, if we have 802.1x configured, for instance, then you're going to have to log on a separate time in order to actually get that IP address. Authentication of the device, not the user. The authentication that we typically think of is when we authenticate ourselves to the network, our username and password. The AP accepts the wireless devices. Okay, you're there, you're a wireless device, and we'll go on and see. The open system authentication device sends an association request to the access point. And again, the default is open system authentication. You can configure it to use a pre-shared key. The only thing that I think would help you with the pre-shared key is if you do that and you try to crack it and you have that set up, it can't get the association because it can't get the authentication. So it becomes a little bit more difficult, and we go back and forth on is it or isn't it. But when you go into monitor mode, you can still intercept the traffic and get the vectors, get the traffic, and eventually crack the pre-shared key. So I guess that we have lots of different ups and downs for all of these things. It's a handshake between the two access points. Shared key authentication accepted into the LAN utilizes the challenge text. The challenge text means that the access point sends a character string. You encrypt the character string with the pre-shared key, send it back, and it decrypts it to see if they're the same. If it is, it allows you on. If it's not, it doesn't, obviously. The open system, basically, if you're there, you're in. The shared key authentication, the exchange of the challenge text. The next is association, accepting the wireless device into the wireless network, and is the final step into joining the wireless LAN. Anybody ever tried to crack a weapon and said that it can't effect an association, can't associate with the network? If you go back to the authentication and set up the pre-shared key, if it can't authenticate, then it can't associate. So you can't have an unauthenticated device that gets an association. It has to go through those processes. After authentication, the AP responds with the association response frame, and it has the acceptance or rejection, reserves memory in the space, and establishes an association ID, and the AID is what you're going to see when you look at the traffic. Response frame includes association ID and supported data rates, so what's going to go on with this thing. Different ways to do this thing. We're going to have distributed coordination function, point coordination function, hybrid coordination function. More things that they can test you on. Distributed, two procedures, carrier sense multiple access, collision detection. Should be collision. Should this be collision detection? Avoidance, shouldn't it? Can we have collision detection in wireless? Not really. So we're going to use collision avoidance or request to send, clear to send. So two different methods, distributed coordination function, which is what you're typically going to see in these things. Channel access methods. Contention, the computers compete to use the medium. Two devices send frames simultaneously to collision, and this actually is contention. It actually is what we use in 802 with the CSMA CD, right? Collision avoidance, we want to avoid the collisions. And are we going to avoid all of the collisions? No. And what these other methods do if we start having collisions, because James talked about the hidden node, somebody on one side or the other can't see each other, can't detect those things, we may have to revert to the CTS, RTS in order, RTS, CTS in order to avoid those things. Collision before the network device sends a frame and listens to see if another device is transmitting. If traffic exists, it waits. Otherwise, it sends, and that's what CSMA CD does. Can't be used with a wireless network, difficult to detect collisions, and all of the stations may not see each other. The hidden node problem would prevent that. Are these nodes hidden?
Well, the two devices are.
The two devices are, and that's what a hidden node is. They're hidden from each other. If it's hidden from the access point, then it's not going to connect, is it?
Nope.
So hidden node, device 1 and device 2 can't see each other. Distributed coordination function, collision avoidance attempts to avoid the collisions. Time when most collisions occurs immediately after the station completes a transmission and everybody wants to get on, kind of like using the phone. If there's one phone and you hang up, even people that didn't want to use it now, don't they? So all stations got to wait a random amount of time after the medium is clear, called a slot time. And he talks about in there the kids, you had the one that cleaned the room and the one that didn't clean the room. So the one that cleaned the room got 2 slot times, the one that didn't clean the room got 10 slot times. And the slot time might be a minute, so the one has to wait 2 minutes, the other one wait 10 minutes. Guess which one's going to get on first? The 2-minute one, right? So the slot time, all the stations get a slot time after the medium is clear, but not everything understands those things. Via explicit frame acknowledgement using the ACK, if the ACK's not returned, a transmission error is assumed and it is retransmitted. And these ACKs, again, are layer 2 acknowledgments, not layer 4 acknowledgments. Block acknowledgement, the AMPDU, we kind of saw that a little bit earlier, that you can aggregate these things, put them together so that you don't have to do them one at a time. Doesn't eliminate collisions because it doesn't solve the hidden node problem. If we do these slot times and tell everybody that's within hearing how long we're going to be using the medium, what about the guy that's not there? They don't know. So if we have issues, you may have to revert to an older method, the RTS-CTS, request to send, clear to send. If you request to send from the wireless access point, is everybody going to hear your request?
Yes.
Really? What about the hidden node?
No, you say from the access point.
Okay, I'm sorry. Well, you would have a request from the access point. I was wrong. If you did a request to send to the access point,
No.
would everybody hear your request? No, but what about when the access point tells you it's okay?
Yeah, I think.
All the stations then should, otherwise they wouldn't be connected, right? So the RTS threshold, the only packets that are longer than the RTS threshold are transmitted, and this goes back to trying to make it a little faster. If significant overhead, if you can do it, what this says is that you can set a threshold and you can send things that are less than that threshold, smaller than that threshold, without going through the RTS-CTS method.
Do that very, like, if you set down, like, really, really low.
Yeah, everybody would have to do it.
Like, you can take
Yeah.
up a lot of bandwidth doing that.
If
You can also use that for
yeah.
troubleshooting, too.
You can say that again?
You can use it for troubleshooting.
You can use it for troubleshooting, absolutely, yeah. You can use a lot of these things for troubleshooting what's happening and what's not happening. What happens if I do this or if I do that. Fragmentation we talked about a little bit earlier, reduces the probability of collision, the amount of time the medium is in use, and also, if you have to do a retransmission, the amount of time it takes to do the retransmission. The receiving station reassembles the fragments. Alternative to the RTS-CTS is a high overhead of the RTS-CTS. SIFS, there's a new term in it, short interframe spacing. And the SIFS is between the frames. It's actually used to send the acknowledgments. It's something that's built in that should allow that. Variations of this thing, CTS itself is used when G devices are mixed with B devices. what happens is the G device just gives itself permission, clears itself, gives itself a clear to send. The HT dual CTS with the 802.11n devices in a mixed environment with the ABs and the Gs. The N device sends an RTS to the access point, which responds with 2 CTSs, one for the ABs and the Gs and one for the N, so that they know not to transmit over the N device. All of this stuff, what's the easiest thing to do here? Probably make everything, just upgrade everything to the N, and then you don't have to worry about the Bs and the G devices doing that. But if you're in an area here where you allow users to bring their own devices, how do you guarantee that they're all N devices or they're all G or up devices? You can't really do that. Do you want to lock somebody out? Somebody comes with a really old machine that's a B, do you want to lock them out? The answer to that one is actually you may want to, because of the reduction in speed that's going to happen on your network. Interframe spaces are intervals between the transmissions, and the short interframe spaces are immediate response actions such as the ACK. The ACK is the most probable one that's going to go into those. Point coordination function is a time used to access the medium after it has been asked and then given approval to transmit. Point coordination function interframe spacing on this thing. And what happens if we enable point coordination function, the timing's going to become different. Point coordination function, they kind of threw that in there. Point coordination function is a process called polling, where the access point asks each of the stations that's connected to it whether it has any data. It's going to slow things down, and the book says, both books that I read said that nobody supports that yet. So it's something that's there that they can test you on, but something that you're probably not going to see. Distributed coordination function, IFS, is a standard interval between the transmissions of the data frames, and that's what's going to allow the countdowns. Extended IFS, arbitration IFS, reduced IFS are all ones that are there from frames extended when frames got to be retransmitted. Arbitration, setting priorities, reduced the amount of dead space required between OFDM transmissions. And OFDM transmissions were used in, we started with the G protocol, didn't we? The A protocol started out with it. B didn't have that capability. This is the frames DIFS, frame A, short interframe spacing, SIFS, DIFS, back-off interval. The back-off interval, that's the amount of time you've got to wait in a frame, and on and on and on as you go through this thing and you go through the process of sending the information. This says time in microseconds. How long are you going to have to wait? What this is saying, station B starts carrier sensing, station B waits. Back off interval 1 and 2. Station A, DIFS, and then frame A, the short, the DIFS, back off interval 1 and 2. Station A waits for station B, and these things based on the timing and the back-off interval. And the back-off interval, the number that you get actually is random after you have waited until the media is clear. And you check to see if the media is clear. The workstation checks to see if the media is clear after it waits for the amount of time that's been specified. Point coordination function, channel access method in which the device is asked in sequence if it wants to transmit, and that will prevent collision because you can only transmit if you've been asked to do that. Point coordination function acts as a polling device. We used to use that in the Navy to transmit target data. You'd have a coordination station which would then poll all. We had a system called the Naval Tactical Data System which collected all the information and was allowed to share it. When we go to AWACS, they did the same thing. AWACS has had a whole lot more information, and they would usually be the coordinating station. In the Navy, when Aegis came about, it became the coordinating station because it had the most data. And what happens is you would go from all of those ships that had joined and airplanes that had joined and were talking in your network and poll them one at a time, and they would send their information. At the end, in our system, doesn't happen here, but at the end in our system, the receiving station, the AWACS, the Aegis, the most capable unit would then send all that information to everybody so that they got their targeting information up to date. This one just asks one at a time. It doesn't redo everything at the end. The point coordinator has to only wait through point coordination function IFS time gap. It's a shorter time gap than the distributed function. Here's no traffic after the time is set. It sends out a beacon frame. Field to indicate that the length of the time will be instead of the DCF. And again, we're going to go through these things. They have different time, different timing depending on what's there. Allows the network to alternate between the polling and the contention method. Hybrid, different types of wireless traffic, different levels, given different levels of priority. So what we're really talking about here is prioritizing traffic. Quality of service. Is that a big deal?
It could be, yeah.
It is now that we're getting into voice, because the voice packets really need to get through. Otherwise, you have some pretty disjointed phone conversations. Video. You kind of would like to watch the movie without having stops and starts. So how do you do these things? Quality of service is what we're
I guess you could
talking about in these things.
The routers or access points, kind of like the conference rooms that have
Yeah.
to
Yeah, to do different, yeah, and you can configure the different ones. A hybrid, what's the priorities, what time slots, but what you're really talking about in the hybrid is quality of service. Do we want to do that? Probably. So, I know this one is pretty dry, but it's something that you really need to know about, and if you take the test, it's something that they're really going to ask you about. What's this one, what's that one? And if you go through, and you should go through the certification questions, and you guys were looking for the one on the internet, right? Same questions in the homeworks, honest, except probably even the same version. The only one that I saw in the 105 was the actual test, and I used the actual test to create those cert questions.
Yeah,
So,
$175.
for what? For the test? Yeah, I know it's not. Now, what you have to do if you want to take the test, and we had this conversation earlier, he said he'd have to go and see if they will subsidize it because of a lot of different reasons, but you need to ask Mr. Geis if they will subsidize it if you're really serious about taking it. That's what all these tests cost. What does Cisco cost? Cisco's are like $250.
Yeah,
They're more. What do Microsoft's cost? I think they're $150. The key to Microsoft tests are, as long as you're a student, you get a student discount, which is a 50% off. It's 50%. It comes out to like $65. Yeah, yeah. When you're using your vouchers, my recommendation is that you use them for all of these other ones that are okay, the Cisco's, the CompTIAs. CompTIA tests aren't cheap. Security Plus, like $300-something. So you're getting a good deal with those vouchers. Anyhow, back to this summary. This is, again, not the most interesting thing. We started out and kind of logical. It's just a matter of putting what these things are. The BSS, EBSS, IBSS, the systems, the networks that we're talking about, the basic service sets. Basic service set is an access point. Extended is more than one. Independent is when we're using ad hoc mode with the computers themselves. A service data unit is the data that comes from the layer above. And then we're going to encapsulate, it's going to become a protocol data unit. And we went through what the protocol data units are that these things use. The differences between the N's and the A's and the B's and the G's, all of these things, there are lots of different mechanisms built into the wireless. If you have a mixed mode, what's going to work, what's not going to work. If you have an N network, it appears to me that what you really want to use is an N network, because it really would be nice to use the 300 megabits per second instead of having to fall back to one of the lower data rates. And then how you're going to keep each of these from overriding or stepping on one of the other ones. The main MAC frame types were management frames, control frames, and data frames. Management frames got you on, control frames did the assisting and delivering, and the data frames had the data itself. And the data frames have data frames with data and data frames without data. The data frames without data are going to show up as null. You should see some of those when you do these things. Discovery by passive or active scanning. Passive scanning, we turn it on and they show up. The beacons are sent by the access point. Active scanning, we're looking for a specific one. Once it's discovered, it requests to join the network, a twofold process, authentication, and authentication, again, two types of authentication, pre-shared key and open system. Open system's the default. Authentication just says, yes, you can get on the network. It doesn't say that you can actually use the network. And that's kind of correlated to an Ethernet network of plugging the computer into, plugging the cable into the switch that goes onto the network. And once we got authenticated, then you had to get an association. One of the other things that I have seen in trying to crack web, just out of curiosity, to do different configurations, if you use a MAC filter, can't associate. And you have to get the association before those processes work. Can they find a MAC address and set that on the one? Yeah, it just takes a little longer time. And back to security. Security is just a matter of making yours less attractive than the next guy's. The different coordination functions, distributed is what we mostly use. The hybrid coordination function, quality of service, the point coordination function, polling, not supported by most or any manufacturers yet. Questions? I know you're ready for me to quit, so I will. Go ahead and take a break. When you come back and you start doing the activities, the backtrack DVDs are up here.